What I would like to talk this morning is just a review the Java virtual machine instruction set. This is very interesting because, I spend lots of time implementing the in Java just to learn what the Java is. And the real reason was that I look at the Java instruction set and thinking I'm looking at a fault machine, okay? And it's so I just want to share my my looking into the instruction set, and I think with that instruction set I can really do a real machine instead of a Java machine. Okay, so what I want to briefly show you is the instruction set, and so in this specification, it is a very good description of the entire Java fault machine. And the Java fault instruction set is extremely interesting because if you look at this instruction set, it is a fault machine. And
we are able to see your screen, Ting.
Oh,
it's working.
Let me see. Okay, let me just give up the screen share.
No, it's working.
Yeah, really? Okay.
Yeah, we see a screen from docsoracle.com.
Okay.
It's scrolling now. If you stop,
yeah, let me just go ahead and show you the summary of opcodes. Okay, let me see if this computer would cooperate. The instruction set really specifies a fault engine, and because lots of instructions are what we are familiar with. Dupe and swap, there's a dupe and swap and to dupe and all these things. So this is a very interesting reading. Here it's a summary of all the instructions by its opcode. It is bytecode. So all the there's only 205 instructions specified. So they fit really nicely into 1 byte. So here, for example, there are 3 columns. On the left, it's a column of constants and loads and store. Okay, constants, you have -1, 0, 1, 2, 3, 4, 5. That's very nice. And you have a long constant and the floating point constants and the double constants, the double floating point. So these are very convenient. And then there's load. It has lots of instructions which loads information into the registers, into the internal. And there are 4 local registers that you can load the stuff in. And then you can write things out from these registers. And I store, long store, F store, D store, and A store. That's a reference store, which my understanding is the references are just addresses of various objects. So you can see there are several important data types. The most important is integer, 32-bit integer, and the long is for the 64-bit integer, and the floating point and the double floating points. So these are the main data type. And they also have Boolean, have bytes and characters and shorts. And so, but most of these type of data are not shown up in the instruction set because all this data are basically converted to integers. And it has a very extensive instructions to operate on integers. And so you convert everything into integer and use this instruction to manipulate that. And here, the stack we all love, it only specifies data stack, okay? But it has a very, not many instruction, but just enough instruction to manipulate items on the stack. You can pop 2, you can drop, pop is drop, pop 2 is 2 drop, and dupe 2 is 2 dupe, and dupe x1 is tuck. Dupe x2 is tuck 2 level deep, which is strange, but they have them. And the math instruction, of course, is very extensive. Basically, it is a complete set for integers. You can add, subtract, divide, negate, shift left, shift right, and or exclusive or. So it's a very extensive, very comprehensive set of instructions that you need to do most of the work. And of course, it can do most of the operations on the long integers, on the floating point, and double floating points. So because it has all these various different types, you have to be able to convert them between integers to long, integers to floating, integers to double, and so forth. So there's a lot of instructions to convert different types of data. And then comparison, basically you do the conditional jump. If else then, if equal, if not equal, if large than, if greater or equal, and dot, 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 dot. The references, I still don't fully understand them, but I would take that the references are basically addresses, but Java is very careful about different types of information. So you have to use the right instruction for the right type of data. In all these things, I think the most interesting thing to me is invoke virtual. This is just a call. This is the, so you can call other objects or methods. And this is what a real call instruction that I need to implement anything useful. Okay, and then that's the control. You have go to JSR, jump to subroutine, and return. And this is very strange because the jump subroutine, it's like the risk JSR. It's not a jump to. It doesn't use the return stack. It jumped to an address and saved the return address in local variable 0. But the return is to return, you put an address in one of these 4 local registers and call return, and you go back. So this is not very useful. And I think the Java try to to delete these instructions because they are not useful. The invoke is a much more powerful instruction in that it pushes things on the stack frame. Okay, so I think the stack frame, the specification doesn't really specify the return stack and how it should be used. But I figured that the invoke virtual would push the return address in a 4-cell frame on the return stack and leave the return address in the local variable 0 in that frame. So if we just create our return stack so that it would take 4 local variables, push them on the return stack or pop them off the return stack. And I think this way we have a good way to implement a 4th engine on this instruction set. And so here it is the control. There's return. The return, you can specify the return address in any one of the local variables and cause a return and pop off the stack frame. And there are these extended instruction I don't fully understand. I don't see any use for me. And then there are a whole lot of, you can see this runs up to 202. And then the 254 and 255 are reserved for implementation. And 202 is for breakpoint. And so there are about 50 instructions not yet specified. So if I'm going to implement a 4th instruction, 4th machine on it, there are, although the instruction set is quite comprehensive, but there are still things lacking that I really have to have. For example, it has the branch, conditional branch instruction and go to instruction. So you can construct indefinite loop with the conditional jumps. But there's no instruction allows you to construct a definite loop that if you know how many cycles you want to loop, there's no way to specify it here very conveniently. Okay, you have to construct a complicated conditional jump instructions to implement the definite loops. Yeah, so this just give you a review of the instruction set, the Java instruction set. And you can see it's very compatible with a 4th engine. We don't need, most likely we don't need all the instructions, but it would be nice if we can implement all the instructions, including doing the IEEE floating point. But you know, at this point, I'm not going to worry about floating points. I just want to implement everything, mostly the 32-bit integers. If we can run the integer machine smoothly, we can tag on floating point instructions later. But it's just a very I think it is a very clean instruction set and showing a very clean architect. And I think looking at the other instruction set, other other architecture, you can see this Java is really a very good architecture compared to the risk to, don't mention the Intel, but even the PDP-11. This byte opcode really specifies a very clean computer architecture. So I think I'm in the process of implement a fourth using some of the instructions. And I'm writing a simulator to simulate all these Java instructions and use all these Java instructions to construct a fourth virtual engine, a fourth virtual machine. I think it is possible if we just get enough of the instructions working, we can put the architecture into FPGA and actually verify it. Okay, I think that's all I have to say this morning. I was working feverishly doing the simulator.
Dr. Ting?
Yeah, it didn't work, okay, so far. But I think next month, probably I'll have something to show. Okay, let me just stop the share and see if
That
Dr.
will
Ting?
be your fourth day talk, Ting?
Are you able to hear me?
no. On the fourth day.
Okay, so next month is fourth day,
Yes.
and Brad has a question, and then I will blather about day and other thing.
Dr. Ting, can you hear me? One thing you might run into that could be a problem is that if I'm remembering correctly, with the JVM's stack, you have a separate stack every time you go through and invoke. So every call frame is separate, and that may present problems as if you're trying to use the JVM stack as the data stack. I think others who've looked at this problem have typically had challenges with that because you don't have an easy way to preserve it between call frames. You end up having to, it's designed really to be a call frame like a C call frame or a Java call frame. And
yeah. I think this is, I have to deviate from the specification because, the Java really try to localize everything into a frame. Yeah. But in fourth, we want both the return stack and the data stack to be global. So it can be accessed by all the methods, okay? And, these are differences that, that we have to consider. But I'm hoping to construct a fourth engine and using the Java instruction set. And eventually, we will be able to move that architecture and implement all the Java instructions faithfully so that it can actually run Java code. But at this point, I'm only thinking about a fourth engine.
I see. So you're gonna sort of drop that constraint that the frames are separate, or how are you planning to?
So in my design for a fourth engine, the stack frame, both the data stack and the return stack would be global. So the all the method can share the same thing.
Nice. I see, but I believe when you if you try to move on top of someone else's JVM, you'll run into the problem that they actually enforce the separation. But yeah.
Yes. We have to put in the limitation if we really want to run Java code. Okay, thank you very much.
Thank you, Dr. Ting. Any other questions? All right, the rest is silent. Ooh, might be a trivia question in that.
Sorry, this is Liang. Sorry, I have a question. Actually, half a question maybe, because I have implemented something like fourth stack machine in Java using the reflection method, and I think I'll try to dig it up from my GitHub code to share with you here. And what I did basically is just to pass a list of words into tokens, and then I will call the function words through Java reflection method, and then push the result onto the stack. It's just a very simple stack machine. It's not a full fourth in any sense, because I did this because I find that to implement the full fourth will be too much work for non-fourth programmer. So I just create a simplified fourth in my design. And I have done it for JavaScript, PHP, Python, and so on. It's not a full fourth, but it's actually, I think, a good introduction for non-fourth programmer to learn fourth by not implementing fourth. So I'll share my link later, and perhaps get some comments from you all. Thank you.
Yeah, I think it is interesting in that Java really emphasize the objects. So they try to localize everything inside an object. And it has lots of advantages for security and the correctness of the program. So it's a very important, when you have everything localized, it's very easy to provide a very secure environment for the execution of code. But the fourth is much more globalized. So the object, we want the object to be able to interact more conveniently among them. And of course, fourth is not secure. You got all the computer is yours, okay? I own the computer, so I should be able to do everything I want on my own computer. If it crashes, I push a reset button, okay? And so it's not a big deal, but I think it is much more convenient if words have access to all the resources inside the computer. And that's what we want.
Okay, thank you, Dr. Cheng. I guess it's my turn now. Oh my good heavens. First, I'd like to say a word about fourth